In the study of elementary particle, today we are going to discuss a very important concepts of fundamental interactions. In fact, in order to study the decay modes of elementary particles and their other properties, it is essential to have a knowledge of the various fundamental interactions to which they are subjected. In fact, all the phenomena in high energy physics experiments can be explained in terms of the behavior of a few classes of elementary particles, and those particles are governed by only four types of fundamental interactions. So you can say that all physical processes and structures in the universe on all scales of size, from atoms and nuclei to galaxies of stars, can be dealt in terms of the four fundamental interactions, and these four fundamental interactions are gravitational interaction, electromagnetic interaction, strong interaction, and weak interactions. Okay. In fact, in order to explore the nature of any physical force, we proceed on the following to get the answer of some questions. In fact, we want to know what kind of objects or particles participate in this interaction. Secondly, we also want to know how does the interaction depend upon the distance between the two particles. What is the direction of the force? Does these interactions depend on the relative velocity and orientation and other quantum numbers like charge, like color, or not? Okay. We have also in mind to know what are the strength of these forces relative to other. It means if you consider that any one of the force is of the strength 1, then what is the relative value of a strength of other forces, we have also to know in this discussion. Okay. Secondly, we have also in mind that how the interaction propagated through the space. Is there any messenger, or does this effect take place time to propagate, or it is propagated instantaneously? What is the mechanism of the action of these forces? So these are some of the questions which is in our mind to know about these four fundamental interactions. Actually, when we will discuss these interactions separately, then we will know everything regarding a particular interaction. But in this lecture, I am just giving you just an overview, and we will deal only gravitational interaction in detail, and the last three interactions will be detailed and discussed in the forthcoming lectures. So this lecture is just aimed to give a basic concept of these fundamental interactions and the detail of gravitational interaction only. In fact, when we will discuss these fundamental forces, then as I have told you, there are some questions regarding these fundamental interactions. Then you will see actually that the strength of various interactions span 39 powers of 10. It means if you consider that the strong interaction has a strength of 1, we consider that a strength of a strong interaction is 1, then in comparison to this strong interaction, what will be the strength of gravitational interaction, what will be the strength of electromagnetic interaction and weak interaction, you will see that if we consider that the strength of the strong interaction is 1, this is just a relative value, then in comparison to that, the strength of the gravitational interaction will be 10 to the power minus 39. Okay. So in this way, we simply say that the relative strength of various interactions span 39 powers of 10. Again, it is seen that all these interactions depend on distance. But how? We will see that among these four fundamental interactions, some are short range force and some are long range force. For example, this weak interaction is a very short range force. You will see that it will be effective only when the distance between the interacting particles is just of the order of 10 to the power minus 18 meter. Only then this weak interaction will be effective. Similarly, this strong interaction, or you can say the strong nuclear interaction, this is effective when the separation between two interacting particles is of the order of 10 to the power minus 15 meter. So commonly we simply say that the strong interaction and the weak interaction are actually the short range forces. On the other hand, we will see that the gravitational interaction and the electromagnetic interaction are long range interaction. It means these two forces will vanish only when the separation between the interacting particles is infinitely large. Okay. So gravitational interaction and electromagnetic interaction, we commonly say that these are the long range interaction. On the other hand, a strong interaction and weak interaction are actually short range interaction. Okay. So simply we say that the distances through which they are effective are also very different. Okay. Now, among these four interactions of nature, we have included gravitational interaction. But as long as you are talking about the nuclear physics or the interaction between the elementary particles, this force is not significant, because we know that this gravitational force is a very weak force, and when we talk about the gravitational force between nucleons or between the elementary particles, then if you consider that what will be the force between the two elementary particles which is separated by just a distance of how much? Just a distance of between two nucleons. Yes. If we consider that what is the gravitational force between two nucleons, okay, then we see that the gravitational force between two nucleons, let us consider this is neutron and this is proton, and we find the gravitational force and say this is Fg between the two nucleons. And at the same time, we also find the nuclear force, that is a strong force acting between them. So if F is the, or you can say Fn is the nuclear force acting between these two nucleons, then it is seen that this Fg is actually negligibly small in comparison to Fn. But if the separation is actually increased, even we make the separation between these two nucleons just let us say 1 mm, then it is seen that the situation is just reverse. It means in that condition this Fg is much greater than Fn. It means this strong nuclear force acting between two nucleons decreases very rapidly, very fastly with the increase in distance. So it is effective only when the separation is of the order of nuclear diameter. Okay. But Fg is actually a long range force, so it will be effective when separation will be 1 mm or more than it. So as long as we are considering the nuclear physics or high energy physics, in that condition this Fg will be negligibly small in comparison to the strong nuclear force or weak force. So in that condition, we do not take into account this gravitational force. Okay. Now, what are the roles of these forces in the uh, determination of the behavior of this nature or the universe? We will see separately when we will discuss each and every interaction in separate manner. But as I have told you in this lecture, I am just giving you an overview of these interactions. So we will see that the structure of the nuclei are determined by the properties of the strong interaction. Remember, the strong interaction gives the idea about the structure of nuclei, while the structure of atoms are determined by those of electromagnetic interaction. Okay, a structure of nucleus, this is determined in terms of a strong interaction, and you should remember that the structure of atoms are determined in terms of electromagnetic interaction. Okay, and as I have told you that in the case of nuclear interaction, this gravitational force does not play any important role, because gravitational interaction is not significant for elementary particles on a small scale. Okay, because on a small scale, that is at a separation of nuclear radius or nuclear diameter, this force is much smaller between acting between two nucleons in comparison to the strong force. Okay, so in this condition, this gravitational force is never taken into account to discuss the nuclear phenomenon. Okay, but when you talk about the large distance or or you are talking about the phenomena governed by on large scale, just as a formation of galaxy by the stars, then actually this gravitational force plays a vital role. That is the dominating force in that condition. So we simply say that gravitational interaction is not significant for elementary particles in a small scale, but it is dominant one on a large scale. Okay. So while we will study the interaction between elementary particles, this gravitational force will never come into picture. But if you discuss the problems of large scale, like the problem of general relativity and the formation of stars, formation of galaxies, or interaction between two planets, or interaction between planets and galaxies, then this force will only be responsible, and we describe all those phenomena in terms of gravitational interaction. But in nuclear phenomenon, this gravitational interaction plays nothing. It has no significance in this condition. Okay, I hope you are getting the things which I am telling you. Now, as I have told you that the strong interaction determines the structure of nuclei, the electromagnetic interaction determines the structure of atoms. Okay, so definitely you have a question in your mind, that what is the role of weak force in the structure of the matter. In fact, you have studied the process of beta decay, and you have seen that when the neutron proton ratio in a nucleus gets altered from stability, it means the ratio of n and p which is required for stability, if by any region this ratio is get altered, or due to any perturbation, the nucleus has a ratio of n and p which is different from the ratio required for the stability, then you know beta decay takes place. And what is the cause of beta decay? What is the interaction between the nucleons which causes beta decay? Definitely, I have told you earlier in that lecture that actually this beta decay takes place due to a weak force. So this weak force or weak interaction is actually responsible for the process of beta decay, due to which the nucleus gets stability. So the role of weak force in the structure of matter is apparently that of minor perturbation that sees to it that the nuclei with inappropriate n by p ratios undergo corrective beta decay. Okay, so what are the roles of these four type of interactions? I have mentioned you in very short. You know, the gravitational force is responsible for the uh, uh, formation of galaxies and stars. On the other hand, a strong force is responsible uh, for getting the information about the structure of nuclei, and electromagnetic force. By means of electromagnetic force, we can study the structure of atoms, and this weak force is responsible for the study of the phenomena like beta decay. And so these are the important uh, function of these four interactions. Actually, in this lecture, I am just giving you all these informations regarding these four fundamental interactions in just a tabular form. And as I have told you, we will discuss all these interactions separately, individually in the forthcoming lecture. But just in tabular form, I am giving you the important informations regarding these four types of interactions. So see this table. In fact, in this table you can see, we will see what are the four fundamental interactions, and then we will see that these fundamental interactions are affected by which particles, what is the range of these fundamental interactions, and what is actually the relative strength. And as I have told you that you will see that any interaction is actually mediated by some particle. Definitely, during any interaction, according to the field concept, a particle is actually emitted or get absorbed, and that particle mediates the particular interaction. So what will be the exchange particle in these interactions, we will also see in this table. Okay, and finally we will see what is the role, what is the work of these interactions in the universe. So see, first of all, we see gravitational interaction. Actually, gravitational interaction affects all types of particles. That particle may be a charged particle, that may be a neutral particle. Every particle, from elementary particle to a big body, a large body like a star and galaxies, all are affected by this gravitational force. Okay, and what is its range? As I have told you that this gravitational force is effective even at a very large distance. So we simply say that its range is infinity. Okay, and relative strength. As I have told you, you can see this table that we have assumed that the strength of the strong force we have considered, it is 1. This is just a relative value. So if we consider that the strength of a strong force is 1, then comparison to that, the strength of this gravitational force will be 10 to the power minus 39. This is its order. Order of something will be multiplied here. This will be 10 to the power minus 39. And this fact I have mentioned earlier. Now, this gravitational force is mediated by a boson, a particle which is actually called gravitons. In the previous lecture, I have told you that this graviton is actually a massless boson having a spin 2, but it has since this gravitational interaction is very weak, so this graviton has not been detected in experiment till date. Okay, and what is the role of this gravitational interaction in this universe? In fact, its role is to assemble matter into planets, stars, and galaxies. This is the important role of this gravitational force. Okay. Now the second interaction is electromagnetic interaction, and this electromagnetic interaction affects only charged particles. Electromagnetic interaction affects only charged particles. No neutral particle, chargeless particle will be affected by this electromagnetic interaction. And like gravitational interaction, its range is also infinity. It means it will be effective when the separation between the two charged particles is very large. Even then, electromagnetic interaction is effective. And when you will compare the strength of this electromagnetic interaction with the strong interaction, then it is found that it is in fact weaker than the strong interaction. And if you consider that the strong interaction's strength is 1, then the strength of electromagnetic interaction will be of the order of 10 to the power minus 2. It means it is almost 100 times weaker than the strong force. Okay. And when electromagnetic interaction takes place, this interaction is mediated by a particle which is called photon, and actually this photon is also a boson. Its rest mass is 0, but its spin is 1. Graviton's spin was 2, but the photon's spin is 1, as you have studied in the previous lecture. Now, what is the role of this electromagnetic interaction? In fact, its role is to determine the structure of atoms, molecules, solids, and liquids. The structure of atoms, molecules, solids, and liquids. The structure of these things are determined in terms of the electromagnetic interaction. Okay. So I am giving you just an information in tabular form regarding these 4 types of interactions, and you should remember it. Now the third interaction is weak interaction. And what particles will be affected by these weak interaction? In fact, this weak interaction affects quarks and leptons. Quarks and leptons are affected by this weak interaction. And what is its range? I have told you earlier that actually this weak interaction is effective only when the interacting particle is at a separation of the order of 10 to the power minus 18 meter. So it is a very short range force. Weak interaction is a very short range force because it will be effective only when the separation between the two particles is of the order of 10 to the power minus 18 meter. Okay. And what is its relative strength? Its relative strength is in fact of the order of 10 to the power minus 5. You can see, if we consider that the strength of a strong force is 1, then compared to that value of 1 of a strong force, it is of the order of 10 to the power minus 15. It means you can say that this weak interaction is almost 1 lakh times weaker, 1 lakh times weaker than the strong force. Okay. Now, when weak interaction takes place, what is the mediating particle? What is the particle or what is the quanta which actually mediates this weak interaction? Actually, the intermediate bosons, you have seen W plus, W minus, and Z0 are the intermediate bosons which actually mediates weak interaction. Okay. Now, what is the role of this weak interaction in this universe? We say that this weak interaction mediates transformations of quarks and leptons and helps to determine the composition of nuclei. Okay. So this is the important role of this weak interaction. What is the role? I am just repeating the same fact. It mediates transformations of quarks and leptons and helps to determine the composition of nuclei. Okay. Now finally, this is the fourth interaction, which is called a strong interaction, or you also call it a strong nuclear interaction. Actually, this is the interaction uh, between the two nucleons inside the nucleus. Okay. So this strong interaction affects actually two types of particles. First one are actually quarks, and the another is hadrons. So quarks and hadrons are affected by this strong interaction. Okay. And actually this strong interaction is also a short range interaction. It will be effective only when the separation between two nucleons is of the order of 10 to the power minus 15 meter, that is of the order of femtometer, 1 femtometer, 1 fm. Okay. And the strength, I have considered that its relative strength as 1, and comparison to this one I have mentioned the strength of other interactions. So its strength is assumed here 1. This is just assumption. Okay. Now what are the particles which actually mediate this strong force? Actually this strong interaction is mediated again by two particles. As you have seen that a strong force actually affects quarks. So when the strong force will affect quarks, then this force is mediated by gluons. And when it affects hadrons, then it is mediated by mesons. So you can simply say that gluons and mesons are the field quanta which actually mediate this strong interaction. Okay. Now what is the role of this strong interaction in this universe? You can see I have mentioned it here, that this gluons or this quarks, actually this gluons holds quarks together to form nucleons. It means so the name gluon, this just acts like a glue. In fact, by the combination of quarks, nucleons are formed. Okay. And that combination is actually accompanied by the strong interaction. And similarly this mesons holds the nucleons together to form atomic nuclei. Mark this. Quarks combine to form nucleons, and nucleons combine to form atomic nuclei. And for that this strong interaction is responsible. Okay. By the combination of quark, nucleons get formed, and by the combination of nucleons, nuclei get formed. Okay. So the formation of nucleon and formation of atomic nuclei, these are actually due to the strong interaction. So I hope by this tabular form you can remember all the important properties of these four types of interactions. And as I have told you earlier that in this lecture we will see only a detail of the gravitational interaction, not the other three important interactions which are actually the interactions of nuclear physics. Gravitational interaction has no importance, no role when you study actually the interaction between elementary particles, but as it is one of the fundamental interactions, so we will see something regarding this gravitational interaction in this lecture. And then in forthcoming lecture we will separately discuss the other three interactions, that is the electromagnetic interaction, weak interaction, and the strong interaction. So let us see something regarding this gravitational interaction. In fact, you know, as I have told you earlier, that this gravitational interaction is a long range interaction, and one thing you should definitely keep in your mind, that this gravitational force or gravitational interaction is always attractive. It is never negative. It is never repulsive. This force is always attractive. Okay. And This force does not depend on the color, size, charge, velocity, spin, and angular orientation of the interacting particle. When you say color, don't think that this word color means ordinary color like green, blue, yellow. Not, no. In fact, color is just a quantum number. When we will actually study the uh, quark model, then you will see that color is just a quantum number, just like a spin, just like isospin, just like strangeness, just like that. This color is also a quantum number. Okay, so this force does not depend on the color of the particle, size of the particle, charge of the particle, velocity of the particle, spin of the particle, and its angular orientation. Okay. In fact, this gravitational interaction has basically three theories in physics. First one is actually classical theory, or you can say Newtonian theory of the 17th century. You know, you have definitely studied the famous universal law of gravitation proposed by Newton. So when you think about the gravitation, there are three theories regarding this. First one, as I have told you, was proposed by Newton, which is called universal law of gravitation. The second one is the theory of 19th century, actually when Einstein proposed the the general theory of relativity, not 19th but the 20th century, you can say. And finally, the modern theory, which is on the basis of the field quanta, we will see. So, although our aim in this lecture is not to detail discuss any theory, but just as a fact, you should remember that gravitation is described by three important theories. So the basic theory or the first theory for this gravitational interaction was proposed by Newton, and according to Newtonian theory of gravity, this gravitational interaction depends only on the magnitude of inertia of the interacting particle, that is the mass of the interacting particle. Okay, you have definitely studied if 2 point masses m1 and m2 are at a separation of r, then the magnitude of the gravitational force acting between them is simply given by F equal to g into m1 m2 over r square. Okay, so this force only depends on the masses of the interacting particle, that is inertia of the interacting particle, and the separation between them. This g is called universal gravitational constant. Now, if you are talking about this gravitational force in context of the nuclear phenomenon, for that we will find the magnitude of this force between acting between two nucleons separated by just a nuclear distance. It means you consider that inside a nucleus there are two nucleons, and the two nucleons are at diametrically opposite points. So these two nucleons will be separated by a distance of just equal to a nuclear diameter, and you know the nuclear diameter is of the order of 10 to the power minus 15 meter. So if you wish to find the strength of this force on the basis of Newtonian theory, what will be the magnitude of the gravitational force acting between two nucleons separated by a distance of the order of 10 to the power minus 15 meter? You can calculate it from the Newton's law of gravitation. You know that Newton's law of gravitation says F equal to g m1 m2 over r square, and this universal constant g has a value 6.67 into 10 to the power minus 11 Newton meter square per kg square, that is in SI unit. And here m1 and m2, these are actually masses of the two nucleons, and roughly the mass of two nucleons will be same. Okay, that is mass of a proton and mass of a neutron, roughly we take it same, and that is actually equal to 1.67 into 10 to the power minus 27 kg. Okay, and R, I have taken the separation between these two nucleons equal to 10 to the power minus 15 meter. So when we will substitute all these numerical values and simplify it, you will see that this force just comes out approximately 2 into 10 to the power minus 34 Newton. And you can see this is a very weak force. When we talk about the gravitational force between two nucleons inside a nucleus, then a gravitational force of the strength almost equal to 2 into 10 to the power minus 34 Newton acts between them. And this is a very weak force. Again, you can see what will be the potential energy or the energy of attraction between these two nucleons. This is first nucleon and this is the second nucleon. You know, gravitational potential energy is given by this formula. You have definitely an idea of this. U equal to minus G m1 m2 over r. Again, you want to find the gravitational potential energy of a system of two nucleons separated by a nuclear diameter. Then let us substitute the values of these quantities. I have substituted here the value of G, value of m1 and m2 are same, and that is 1.67 10 to the power minus 27 kg. Okay, and r is 10 to the power minus 15 meter. So when you will simplify it, you will see that this U will be minus 2 into 10 to the power minus 49 joule. After seeing this value of potential energy of a system of two nucleons inside a nucleus, what do you think? You can see actually this value of potential energy is very low, very small. And so if we want to break the system of two nucleons, or we want to separate the system of two nucleons and only gravitational force acts between them, then we have to supply only an amount of energy from outside, which will be 2 into 10 to the power minus 49 joule. This is almost zero energy, no energy. So you can say that this gravitational force between two nucleons inside the nucleus is negligibly small. It is not of any significance. We cannot take under account this force while discussing the nuclear interaction. Okay? So I have mentioned it here that this value indicates that the gravitational force plays no role in particle reactions. Okay? Now we will see later on that any interaction is characterized by a dimensionless coupling constant. In fact, coupling constant for any interaction actually determines the strength of that interaction. So if you want to know what is the strength of any particular interaction, you have to know the value of the coupling constant for that interaction. When we talk about the gravitational interaction, in that condition we will see that the coupling constant of gravitational interaction is a dimensionless number, and it is defined as gm square over h bar c. Gm square by h bar c. Here m is actually mass of a nucleon and g is universal gravitational constant. H bar is reduced Planck's constant and c is speed of light in free space. So let us substitute the numerical values of all these quantities. You can see when we will substitute the numerical value of all these quantities, I have substituted here, and you will simplify it. You will see that this coupling constant comes out to be 5 into 10 to the power minus 39. Minus 39. Can you imagine what is this value? Actually, you can see this dimensionless coupling constant for the gravitational interaction is very small. It is a negligible number. It is almost zero. It is this number 5 into 10 to the power minus 39 is very close to zero. So this is almost zero. So we simply say that in case of nuclear interaction, remember here mass of nucleons have been taken. It means you are talking about the gravitational uh, force, or you are talking about the coupling constant for gravitational interaction in case of nuclear phenomenon, not in the case of galaxy formation, the gravitational force between two planets. You are not talking about that. We are talking about the gravitational force between two nucleons. In that condition, the coupling constant has a value of 5 into 10 to the power minus 39. Okay? And as I have told you that the value of the coupling constant determines the strength of an interaction, and since the value of this coupling constant for gravitational interaction regarding the nuclear phenomenon is much smaller, it is negligibly small, so we can simply say that this gravitational interaction can be neglected in most of the nuclear effects. So I have mentioned it here that it is so small that it can be neglected in most of the nuclear effects. There is no need to take this gravitational interaction under account. Sorry. Now, as I have told you that the another theory of gravitation was proposed by Einstein in his famous general theory of relativity. In fact, according to Einstein's idea, this gravitational force propagates by fields and space wrapped for particular effects. Actually, the space-time curvature is responsible for the gravitational attraction according to Einstein's theory of gravitation. Okay, but I am not giving you any detail of this theory here. Okay, this is just an information. But what is the present concept of this gravitational interaction? As I have told you earlier that according to the present concept, any interaction is mediated by a field particle. And just like, for example, the electromagnetic interaction is mediated by a photon, you know. The weak interaction is mediated by the intermediate bosons. Just like that, this gravitational interaction is mediated by a field particle, and that field particle is called graviton. It means graviton is responsible for this interaction according to the present view. Okay, and so you can simply say in one sentence that this gravitational interaction is mediated by a field particle, and that field particle is called graviton. And as I have told you earlier in the previous lectures that this graviton is a boson, it has zero rest mass and its spin is 2. And since its rest mass is 0, so you know according to a special theory of relativity, if rest mass of any particle will be 0, definitely the velocity of that particle will be velocity of light c in free space. So this graviton has a velocity equal to velocity of light c in free space. Okay, and I have told you earlier that this graviton has been not detected in experiment till date. Why? The reason is that this gravitational field is extremely weak. You have seen, and since it is very weak, so these gravitons are not detected in experiment, because this detection of this field or this force is actually impossible in experiment, and that's why graviton has been not detected in experiment till date. So this was just an overview of the four fundamental interactions, and I have given you some detail regarding the gravitational interaction. But in forthcoming lecture, we will now see the detailed discussion of the remaining three interactions, and those are actually electromagnetic interaction, weak interaction, and the strong interaction. Okay, I think you have enjoyed this lecture, and hope you will enjoy the forthcoming lecture too.